So let me send you a URL.
Yeah, I'm able to see your screen.
Okay. Good. Then let me see. See if we can remember what we did recently. Okay. So let's just rebuild this. So the goal here, let's see, closure subs. So right, the goal is to basically change this from the U00 or this range to just sort of, well, to this kind of.
Right.
And I think so let's update the comment a bit here. Represents a type parameter which will always be a tuple of k different types. These post type inputs. Okay, so
So is the idea that that is a tuple, but inside that U0 to UK, each of them will individually also be a tuple, is it?
no.
Because no, because the struct. Let's say if there is a struct and it has some member variables, then we want to capture exactly like the entire path to the lowermost variable that is being captured by the closure, right?
Yes. We're not gonna do that yet. But yeah, the idea would be that right now each of these types in the tuple will correspond to some local variable. But
Right.
going forward, they might correspond to just the type of some path.
Okay.
And that's exactly why we have to change this, because the number of paths we don't know until later in compilation process. And whereas before we knew exactly how many variables we were going to capture very early. We just have to look at the names. We don't have to look at their types, right?
Right.
Now the only thing here is that this is not legal Rust syntax, right? I think we talked about this before. Like, you couldn't make a struct where you put parentheses in this list.
Right.
I don't think that's gonna be a problem for the compiler. But why don't I think that is a good question.
I think you said something that it's not a real struct or something.
Yeah, that's right. I don't think it's going to be a problem because these are not real fields in the compiler. Like, we don't give them a def ID. And so you can't ask for, like, what is the type of this field?
I see.
If you could, that would be a problem because we wouldn't have a type to give back. Because when you ask for the type of a field, it's always in the context of its declaration. So it can refer to these type parameters, but it can't refer to like sub-elements of this tuple, right?
Right.
So we'll see. Like, it may turn out that I'm wrong. In that case, we'll have to do another refactoring first, where we introduce, where we make this be one field with a tuple, right? To be honest, I actually would prefer if we did that eventually, just because I would like this to map to a Rust struct. It's just sort of nice conceptually, but it would be kind of annoying to do, and I don't know that it's the step I would want to take, like, it might be better to do as a cleanup pass afterwards.
I see. Yeah.
So let's put a note about this, though. Note that the struct above is not legal Rust syntax because the Upvar fields get their type from elements of the UK tuple. We can do this because this struct is not truly represented as a struct in the compiler. Where is it? We might want to refactor to a single field upvars of tuple type, just to be nice. Okay, so let's modify comment. So let's see. So how would we actually make this change happen? Well, the first thing is there's a pass called, or you know about the query system, I think.
Right.
And so there's a query called generics of. You can see it here. And it's the one that says for any given def ID, what is the number of generic type parameters that it has, basically? Or what are the generic type parameters declared on it, right? And so you can see here the definition. It starts out, it has this def ID, and it converts that to a node ID, which is old crap that we still have. It identifies a node in the here, grabs the node, looks at it, and says kind of what is this def ID, basically, right? What kind of thing is it? And the thing we're interested in is this case, where what we have is a closure. So in that case, actually what it's doing here, when it calls closure-based def ID, so this is computing the parent def ID. The idea for the generic struct, I don't know if we looked at that before, I forget, is that it is, here it is. It is, they're actually like a little bit of a linked list, so to speak, of generics, right? So you have what are the type parameters declared on this particular thing, and then it has a parent, and you kind of inherit the type parameters from your parent. So you could think of like a method has some type parameters, and then it's inside of an impl, and the impl might have type parameters, and all of those parameters are in scope in the method, right? So this list is never very long. I think it's usually of length one or two, basically. But we might add some extra levels, synthetic levels, I forget. But it's not very long. In any case, what we want, in the case of a closure, the way we do it is that the closure parameters, the closure's parent is the enclosing function, which may itself have a parent. So a closure inside a method would have like a list of length 3, right? That makes sense.
Yeah.
So here, when we call closure-based def ID, all that does is basically walk up. In case it's a closure inside a closure inside a closure, it walks through the list of closures to find the innermost non-closure, and that's the parent. So,
innermost or outermost?
Innermost, right? So if you have like impl foo, let's say a function bar b, let x equals the y equals the, then and this is the one we want. We go up to the innermost, which is bar. That's going to be our parent.
Oh, okay. Right. And
it, of course, has a sort of grandparent. This is the us, right? Okay. Good. So I guess it doesn't really matter if it's innermost or outermost because there's only one function. But anyway, so right. So then what we do. So now we have the parent def ID, then we match on the actual thing itself that we're computing the generics of. And in this case, it's going to be a... Wait, what is this? Yeah. Oh, I see. In this case, it's going to be an expression because it's a closure.
Right.
So if you look here, you'll see that there's actually no... It goes to the underscore case. And basically here what we're doing is we're computing what are the generics that were in the AST that like the user wrote. What were the generic declarations that the user wrote, right? And so for a closure, there are none because there are no space for them. But like on a method or something, that would be like the AST for this syntax here, right? So this is why we get no generics. And then now what's going on here is we start to do some like manipulations, basically. So what this is doing is counting how many generic parameters came from the parent scope. Because when we give each generic parameter an index, I'm going to make a little buffer for like talking about this. So like if I have like something like this, right? What's going to happen is we're going to assign this the index 0. We're going to assign this the index 1. And so the starting index depends on the parent, right? And this has self thing. This is like in a trait like this. Actually, the self parameter is 0. This is 1. And if you had a method, you know, u would be 2. But anyway, so okay, blah 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 blah. There's some stuff around lifetimes, not so exciting. Here's where we actually create the type parameters. So all of this is like a no-op for closures because this variable AST generics here is going to be an empty list, basically. So we're going to now here like iterate over all the AST generics, but there aren't any, so okay. And here's where we get to closures. So here we have a little special case, basically, saying if this is a closure node, what do we do? And we actually do something slightly different for generators and closures here. But the basic idea, first we add some number of dummy arguments. We're not going to change this code. This is for these like these fixed ones above, right? And if we go back to our declaration, if we go back here, okay. So right there, you can see the correspondence, right? So CK here.
Yeah.
Corresponds to this closure kind here.
Oh, I see.
And so on. So we add those. And now finally here, and maybe it would be nice to add a comment while I'm at it. I don't know what the... where's the generator subs comment? Or maybe there is no corresponding generator subs comment, is there? Okay, that's annoying. Okay. So now here is where we add the right?
Right.
And so I think what we want to do is really, the first thing we want to do is basically take this away and just change this to one parameter, right? That makes sense?
Yeah.
Now we have to change a few other bits of code to match. And then what we have to do is try to build it and watch it die a million horrible, hard to diagnose deaths until we get everything else that I've forgotten about, right? So the first thing we can do, which should be relatively easy now, is we were making this tuple somewhere, right? Here we go. So what we want to do instead is just say, basically that. Right?
Right. Yeah.
Similarly, in the generator subs, we want to just get rid of that. Oh, I guess it is using TCX. So. Okay, it's fine. Okay, wait, that's not everything. So that's one part. I think the rest of the code should just be fine because nobody directly. That was the whole point of the work we just did. Just nobody directly accessed self.subs anymore. We'll find out if that's true. But the next thing we have to do is so before we were editing the generics of query. Now we have to edit the code that when you actually encounter a closure in an expression, we have to assign it a type, right? And that's the code that kind of has to be made to match now because that's going to actually instantiate a reference to one of these closure types, and it's going to create the substitutions array, the subst array, and it has to have one type for everything that came from the generic self query. So now it's going to have too many types, basically, because we're going to have one per upvar, and we just want one for the whole tuple. So, so somewhere in here is this with free vars, I guess. I don't know. Where does it actually? Okay, or not. So let's take a look. Let's read through this code a little bit. Check closure. It's kind of complicated. This part is kind of complicated, but luckily we don't care about it. So what this is doing is figuring out what are the parameter types and the argument types and so on that we expect. And that's not really relevant to what we're trying to do now. So we can just ignore that and go to this check closure function. And you see it takes as argument the expected signature. Like I said, we don't care about that right now. It's going to do some stuff. And here we go. So here, this is the code that's creating the type variables for the upvars. And I think it looks like we don't call with free vars because we just sort of match it looks like we just get the generics that came from that other query, and we just do the same number of things as we're in there. So this will all kind of already work. Let's walk through the code and make sure I'm right. So what identity for item does is it calls subst for item. I'll make an example here. So like example let's say given a struct S, declared like so. What do people normally do? Example, something like this. Struct S A B C. Right. So basically, this returns like within the context, from inside the context of the declaration, it just returns the parameter types.
Nice.
And the idea is you can a lot of times you'll have a mapping like from A to U32, B to I32, C to F64 or something, and you can apply that mapping to this. I don't know if that's it.
Yeah.
Anyway, so okay, so going back, so that was identity for item, and then that gives us this base substitution. Okay, right. For the closure base def ID. So this is the enclosing function. So if we go back to my example, if we had a closure in here, but this is what we're doing is we're getting the self substitutions for the enclosing function, right? So basically base subst will be something, will start out as TU. Okay, that makes sense?
Right.
Actually, it's going to be
Yeah.
T self U because we're in trait. I forget what order self goes in, probably here. But anyway, same idea. And the point of this is those things are actually not changing. Like, we're creating the closure type from the point of view of this spot, so from outside the closure. But inside and outside the closure, we share the same like overall context, right? So these are still, if you ask me like what is the type T in this context, the answer is it's T. It's a placeholder for T, right? For some unknown type
Right.
T. So that's the starting point. And then we call extend to, and here we give it the actual def ID of the closure, right? So we just modified it so that the generics of this are going to be like self T U, whatever it was, closure signature, closure something, and the upvars, right? And the upvars too. So what this extend to is going to do is add in for each missing thing something which comes from this closure, this closure here, this code, right? And if you look at that code, it just creates fresh type variables.
Nice.
So, and we can error out in the case of lifetimes because this is basically what are the extra type parameters we added to the closure, and we know that they're never lifetimes. So this code is all a long-winded way to say that this code should be all fine. Instead of making n upvars, we now have exactly one, right?
Right.
And now this is the generator code. This is fine. What this does is, I don't know what this does. Oh, okay, I see. So this says if we know some stuff about the generator, if you remember, in the case of a generator, we'll actually have like an extra variable in here. So it's going to unify now these three variables. That's what this is doing, right? It's unifying with what we know the yield type to be. That gets unified with the variable that we extract from the substitutions.
I see.
Okay, great. And then we call make closure. And all make closure does is basically in turn the pair of the def ID of the closure with this substitutions that we had here. Right. That's the closure type. And that's the type of our expression. All done. Nobody in here, in this code, actually cares about the types of the upvars, right? So they're just type variables that don't get changed. So far, so good?
Yeah.
So where this starts to change is the Upvar analysis. So this code runs, when we type check a function, this code runs sort of at the very end, I think. This closure analyze function. Let's see. Yeah. So kind of after we've done a bunch of other stuff. Then we come back over, and now we try to figure out the types of the Upvars. And the reason we do that so late is we want to know how those Upvars get used within the closure body in order to decide if they're move or and mute or what. So the details of this, I think we talked about this before, but it doesn't really matter too much how the inference works. Let's see. The important thing is, right, okay. So I'll just sort of walk through it real quickly. So what the inference does, first we get the type of the closure. Okay, that's fine. And we basically pull it apart into the def ID and the substitutions. Right? And of course, the type of the closure had better be a closure, or else something crazy happens. And then for every up variable, we create, in this part of the code, what we're doing is basically in the inference, we're going to keep a little bit of information, which we call the Upvar capture map, about how that variable got used. We start off assuming that it's only read from, so like the most minimal requirement you could put on it, basically. And then when if we see that it's written to, we'll up that to O and it gets mutated. If we see that it's moved from, we'll up it to O and it's moved, and so on, right? But that's all in this like internal data structure, the Upvar capture map. And we don't care about that right now. In particular, I don't think any of this code, let's check, but right, like none of this code touches the substitution. So none of this code interacts with these type variables that we've created. We have this internal data structure. We then, what this code does is it basically walks over the function body, and this is where we're looking to see, oh, this Upvar got written to, oh, this Upvar got mutated, and whatever. Right. And I think it is still true that, well, we're going to find out. I think it is still true that this doesn't interact with the types from that closure substitution. But like those inference variables, it could be that something in here is going to try to call methods on the closure substs and get upset because it's going to find not a tuple of Upvar types, but an uninferred type variable.
I see.
We'll find out. I don't think so, but it might. Blah, blah, blah. This is not very exciting. What this is doing is, once we figure out, this is basically recording whether the closure is fn once, fn mute, or what. We don't care about that. Finally, this is where it gets interesting to us. So here we have the final Upvar types. So these are the types that, now that we know how the variable is used, we can compute a type for each of the free variables, right? So like, we go through each of the variables that are captured. We read information about what we tried to do with it. Did we need to take ownership? If we needed to take ownership, this is then computing the type of the field in the resulting closure. Right? So if we have a variable like some vector vec 1, 2, 3, and then we have something like another vector 4, 5, 6, and we have some integer 22. Then, and let's say that the closure does stuff like this. It sort of drops some vec. It pushes a value here, and it prints out some integer. Then the resulting, this is going to be by move, this is going to be by mute, and this will be like by shared reference. And the resulting closure struct would have, so the resulting types, let's say, of the captured upvars would be, for some vec, we'll just capture that just like it is. For another vec, we'll have a borrow, right? And for some integer, we'll have a borrow as well, I think. So that's what you see going on here. Right? If it's moved, this is computing for each upvar what is the sort of type, starting from the type in the parent, which would be like vec of I32. It'll add an ampersand, make ref. This creates an ampersand type. And it's either the region, nor the region, but it's either ampersand or ampersand mute, depending on whether this was immutable or not. Right? Maybe I'll add some comments here. That makes sense?
Yeah, it does.
Okay, so this is going to compute a vector of types. Now, this doesn't actually do anything with these types, it just computes them. And that's the vector of the final upvar types. So now, at long last, we get to the part of code I'm interested in, which iterates through the types of each upvar and unifies them with the corresponding final type. And this is what we want to change. We want to say something like, how did this work? Make tuple. Okay. We want to, we basically don't have to do this work anymore. We can say, we can make a tuple of these types, and then we can get the upvar tuple type, and we can do this. And that will have the same effect, right? Because that's just how tuples work. Like when we relate these tuples, we'll relate all the types within them. So yeah, that's the right one. Okay. Sound good?
Yeah, sounds good.
That might be. I don't know. Let's find out. That might be everything we have to do. I would be a little surprised. I bet there's some code somewhere else. Probably in the code generator or something. But it might all the other code might go through the closure subst. That would be nice if that were true. Because in that case, we've already done the work. So let's see. So what we did here, we change closure generics to produce a tuple of upvars. Also change closure subst and upvar inference code to match. This did not quite compile because this needs to be an iterator, I guess. And okay, so this type upvar substs. I guess this just doesn't have this method. And I guess this code is sort of dead now. Also, normally we put a space. Yeah, so this didn't work. Why? Okay. Annoying stuff like that. It'd be kind of amazing if this actually worked. That would be cool. So, while we're waiting here, any questions? Kind of ran through a lot of stuff there.
Yeah, no questions. Like, I'll probably revise this video later tonight.
Cool. Okay. Well, we built it builds, but well, that is to say, it type checks. That's not saying a whole lot. Unfortunately, this is not the sort of change where just because it type checks, you know that it's going to work. So I'm probably going to have to go in a little bit. What I'll do is we have a few more minutes, but until then, I'll push this stuff to your branch when we're done.
Sure.
And I think, let's see if we can get to the first ice, because I don't know how much experience you have debugging those. It would be nice if I could show you some of my...
Oh, you think it'll ice out?
Oh yeah, I'm pretty sure it's going to ice somewhere. So what I think is going to happen is some code, I mean if we're lucky it's going to ice. Some bit of code, well, okay, forget that about what I said about lucky, but some bit of code is going to have a mismatched assumption about the set of generics on the closure, right? That it's kind of hard-coded to assume the old setup. And so it's going to try to grab a type variable that doesn't exist or something. At least that's what I would think. But we'll find out. Like I said, it's possible that that actually won't be the case. That would be really cool. The annoying thing, this is what's going to be annoying though, I just realized, is that normally ices are kind of good because, I mean, depending on your point of view, but because they die sort of very early, or they die very easy. It's easy to trace it kind of to where it's dying. But what's probably going to happen is that we're going to get an ice. The first thing we do after we build the new compiler is we try to build libcore. And usually with a change like this, that will die, because libcore actually uses a lot of language features. And that's annoying because debugging, like, if you have a lib standard, it's kind of nice. You can make a minimal example and debug it. But debugging libcore when libcore fails is a super pain in the neck. However, because there's a whole lot of code basically, and it's kind of complicated, and you have to like interrupt the bootstrapping process and so on. But I have a trick. What I usually do is I have a little like what I call the libcore template. Because the thing about libcore is it has some types the compiler kind of needs to know about, like send and sized and so on. These sort of built-in traits. So my core template has like very minimal definitions that are enough to get you up and compiling, but not really right. And then usually what you can do then is when you see an ice, you sort of copy and paste just enough to reproduce the ice into this core template. and then you can debug against that, which is a lot less code and a lot more tractable. So that's one option. Another option is if we could make this change conditional, like maybe we make it, that would be a little annoying to do, but I guess not so hard. You could imagine passing in a flag to the compiler to tell it to use this new code. And then we'd have to go back and undo some of the changes I just did, or make them check a flag to decide which version to do. The nice thing about that would be then, when it builds libcore and stuff, it's going to use the old style. And when you build a new example, it'll use the new style. But I think that would probably wind up, that would be annoying, and I think it would probably get us in trouble, now that I think about it, because it would break, because then code that was compiled from libcore has a different structure than code that comes from the current crate we're building. Like when you use this flag, closures are set up differently. And that might cause problems, I don't know. So I probably wouldn't do that, actually. But we'll see. Anyway, what I would recommend is, as a side note, is to build with the incremental option. I don't know if you already do that. But
right, yeah.
Just because, at least when I'm debugging this sort of thing, what I always do is turn on the Rust logs, dump out a bunch of information, and inevitably you have to add some more Rust logs. And then that's where the incremental builds are really nice, because you can kind of get your get the output of your new debug printout much faster.
I see.
Although they do take longer.
So this libcore template that you were talking about, you create it and you replace it in
No.
lib.
I mean, I did create it, yes, but I don't replace it in the repository. What I do instead is, I have it. I'll send you it. It's on GitHub somewhere. But I basically just what directory is this run? You would just sort of do this. You would just kind of build it. Oh, that's interesting. Oh, yeah, just ignore that. So that's some weird problem. I don't think that's actually our fault. My computer has some kind of weird thing that happens. Let's see if it reproduces. But for some reason that I don't know, I get random crashes in LLVM. Nobody else seems to have this problem but me. It's kind of weird and kind of scary.
You have a probabilistic machine instead of a deterministic.
Yeah, I'm not sure if it's hardware. I've tested the hardware a whole bunch of times and never found a problem, or what. But anyway, so by now I know, though, if I see some weird crash in LLVM, I should try it again. It's not only LLVM, but it's usually LLVM. Anyway, the point is you can build this just like so. You just build it like a library. And it's got all these little weird... Let's see, what's that? No, that looks again... It's another SIG-SAG V. It's probably not our fault. Like, we're not even... We're not even running, I don't think. Yeah, we're still running the... We haven't even run our code yet. We're running, like, the bootstrap. The stage 0 compilers. I really wish I knew what was going on.
Can you, like a little bit, tell me about what this libcore does?
What libcore does in general?
Yeah.
Libcore is, so libstandard is the standard library.
Right.
The standard library has some internal crates that it's built from, and the smallest of those is called libcore. And libcore is a special one because it's the only library that is required for all Rust programs. So the rest of libstandard you can opt out of by using the no standard attribute, but you can't opt out of libcore, at least not on stable Rust. We do actually have a flag for it because we need it as part of the bootstrapping process, but the reason that it's required, it's very minimal in some sense. It only has things that it doesn't place any real requirements on the host operating system. but it does have
I
some
see.
basic concepts that are like part of the language. They're like library types, but they're part of the language, right? So like the sized trait. This is where the declaration of the size trait is. And this laying declaration here, this is another unstable thing. That's an internal thing to the compiler saying this is the size trait. This is not just a trait named size, right? This is the size trait. So and all these similarly for these other things. And those attributes can only, well, actually they can be in things that are not core, but there can only be one crate. Like there can only be one trait that is tagged as the size trait in your entire crate graph, and because everybody has to have libcore, it's always this one, right? And it would be unstable, obviously. It would be like you're not. These basically are not meant to be used by normal Rust developers. Yeah, so that's the role libcore plays. That's why it's special, and why you kind of want this minimal set of things so that the compiler can actually start up and get going. Like without these laying items, it dies pretty early because it has no size trait. You know. And to be honest, this is probably out of date. Like I basically adjust this every time that I have to debug something in core. And I kind of, luckily core doesn't change very much anymore, but it may be missing a few things, or sometimes you have to tweak it because something changed. But, okay, all right. I'm gonna probably leave at this point because I have another thing, and it looks like I'm building LLVM here, so that's gonna be a little while. But I'll push this, and we'll see what happens. If it does die, we can chat over Zulip about how to debug it.
Sure, yeah. Sounds good.
All right, cool. Talk to you later.
All right. Thanks a lot for your time. Yeah, talk to you later. Have a good weekend.
You too. Goodbye.